Okay, this is my second pre-recorded lecture. First of all, I would like you to have already viewed the video lecture 1 from MIT that gives kind of an introduction to radar and talks about some of the things that can be measured with radars and some of the types of systems and some of the variables used in radar. And that'll kind of give a background to what I'm going to cover here, which is to fill in some of the details of the radar equation. Okay, so assuming you've already seen that, this is a picture from those notes, and these things are in a little bit different order than what was presented because I want to use this for my purposes in deriving the radar equation. But your basic radar problem looks like this, where our goal in using radar is first of all to detect something, something that will reflect an electromagnetic wave in the microwave frequencies. Typically something has to have some metallic or conducting properties. And in addition to reflecting that back and giving us a detection that something is present, we can also measure the range to that target by looking at the time that it takes a transmitted pulse to leave our radar, reflect from the target, and then return to our transmitter. And again, ignoring some of the changes in the medium in which a signal propagates through, we can measure this range as being the range as being 1/2 of the total path traveled by the electromagnetic wave. So the speed of light times the time of travel, the round trip time, measured from when the transmitted pulse is sent out to when the transmitted pulse returns, divided by 2, because it's a round trip time, gives us a range. So we already saw that radars can be used to detect, to see if there is something present in some area, and also can be used to measure a range. And if you looked at the notes from, or the lecture that was pre-recorded from the MIT website, you can see that we can also not only find range, but looking at the Doppler shift, which I believe I discussed Doppler earlier in the course, we can find a range rate. We can also look at how strong that signal is when it's returned, so it gives us some measurement of how much that target reflects the signal, which can indicate a couple of things. One, it can indicate what kind of material that target is made out of, if it's made of a very reflective material or if it's made of a very absorbing material. That can also tell how big the target is. When I derive the radar equation, we'll see that the area of the target plays a very similar role in the radar equation as the effective area played in our communications link budget. And the radar equation is going to be very similar to the communications link budget. We'll determine that quantity is going to be called the radar cross section, but the cross section can tell us some indication of what that object is, also in combined with all of these. So a large aircraft will have a different cross section than, say, a small drone. By combining the cross section with the range rate, we can detect what those objects are. Now, I should say I'm discussing radar here, and so far all of the notes I've looked at from the MIT course have discussed radar in the sense of I have some finite extent object there, so I can describe it as some effective area. The other use of radar, and actually most of my work where I use something like radar, is when I'm not looking at a target, but I'm looking at a small section of a large area. So that may be, if for not really maybe in this configuration, but if I have radar from an aircraft or a spacecraft and it's looking at the ground, so I have a radar looking down and I'm sending my pulse out, and then I have, say, the ground or the ocean, I'm going to get a reflection back from all of these points I illuminated. And that effective area is going to be a property of two things. It's going to be, first of all, it's going to be very dependent on how much of the surface I illuminate. So that's going to be set partially by my beam, my radar beam, how I detect those pulses, and that's my next lecture I'm going to cover is how we actually do the signal processing to measure this time delay, as well as the material that is made of. And I'd like to separate those two things. So in this type of case, we might use what's called the normalized radar cross-section, and that's sometimes given by a sigma naught. And that is basically the radar cross-section divided by some area that I'm illuminating here. So it's a scattering cross-section per unit area, and of course that is non-dimensional. All right, so that's the other use of radar cross-section. But in all of the examples I'm going to present now, and in the lecture that's pre-recorded from MIT, we're dealing with a target that is a finite extent discrete object. Okay, so the next lecture that I'm going to give in person on Wednesday, I'm going to talk about how we measure this time delay. We'll look at how that accuracy of measuring that time delay depends upon the properties of the pulse. And you might imagine one of the properties of the pulse it depends upon is how strong the signal is. And you also might imagine that the ability to successfully detect anything is going to depend upon how strong the signal is as well. And this is, again, very similar to the problem with the bit error rate when we talked about the communications link budget. So if I go back here, and again, taking the slides from the MIT course, and if I look at just recording what's transmitted, what's received by the radar, and I transmit a pulse, and it's going to have some finite length. So this is time, and this is some measurement of power. So I design in my radar a pulse, and then at some period I see my return, and then this, of course, this time here is my time of round trip. So there's a few things we want to keep in mind. Obviously, I'm probably going to use more than one pulse. I'm not just going to turn on a radar and take one look at what's out there. Radar is going to operate continuously, so I want to keep sending pulses out automatically. So this pulse repetition rate, or pulse repetition interval, 1 over the pulse repetition rate, is going to say the maximum time or the maximum distance in which I can unambiguously resolve a target. Because if my time that it takes my pulse to get to follow its round trip path is longer than my pulse repetition interval, then I don't know whether this is my tau or this is my tau. Okay, so one of the design parameters in the radar is to look at the maximum range that can be unambiguously detected. That's set by the pulse repetition interval. Let's see. Okay, and so some other things as far as the power, duty cycle is the ratio of the length of the pulse over the pulse repetition interval, and pulse repetition frequency is 1 over pulse repetition interval. Okay, but this is a really nice drawing here, but it's kind of ideal because I have no noise in it. So I always see in this little simple drawing with no noise, I can see my target. A more realistic situation is going to look like something like this, where if I just am listening with my radar, whether or not I've transmitted a pulse, I'm going to have some non-zero signal coming into my detector. So if I send out my pulse and then I see my received pulse, I'm going to hope that in order to detect that has to be somewhat above the noise. Okay, so we get the idea, and next class I'm going to try to quantify that But you get the idea that this is very similar to when we're looking at detecting the bits, right? We looked at an energy per bit as our ability to detect the bit. So there's going to be two things we can look at. One is, again, very similar to the energy per bit. One is the length of time of this pulse, right? If I have a longer pulse, I can look at the signal for a longer period of time and determine whether I've seen a return or whether I'm just seeing noise. And the magnitude of the pulse, which is going to be proportional to the magnitude of the return, and how that is relative to the noise. Because there'll be always, since noise is a random quantity, I could always accidentally detect that as a return. So I get the idea that predicting the signal to noise ratio is going to be an important consideration for the performance of a radar system. Okay, so actually I should have just gone to the next one because it actually shows what some possibilities are if my signal to noise ratio is too low. So I'm going to set a detection threshold. Say, okay, if I see a return above this power level, I'm going to identify that as a target. And the red is the noise, and so I see I have two possible errors. One is if I set my detection threshold too low, there's going to be a probability that my noise gives me a false detection. Of course, there always will be a probability my noise gives me a false detection. It's just, what is that rate? The bit error rate in bits, analogous here to my false alarm rate on detecting a target. This is what I would hope to see. If there is a target, the return is going to be high enough above the noise that I have a range of detection thresholds that will allow me to detect it and not give me a false alarm. Of course, if I raise my detection threshold too high or my target has too low of a signal noise ratio, I may miss it. Okay? So signal to noise is going to be an important quantity, just like it was in the communications link budget. And now we're going to look at a link budget for radar, or what's called the radar equation. Okay, so I think since I want to make sure all this stuff is recorded properly, I think I'm going to pause now, and then I'll pick up in the next